So hello, welcome everyone. So today we have Benjamin Landon from MIT. He will be talking about universality in random matrix theory. So Ben, you can take it away.
Thank you very much for the invitation to speak here. The purpose of today's talk is just to give, excuse me, a bit of an overview of what universality in random matrix theory is, and then just some of the ideas behind some of the proofs in the strategy pioneered by Erdős and Yao in around 2008. And then maybe if we have time, get to some of the more recent developments as well. So I'll start off just with one slide telling you about some of the original historical motivations for studying the kinds of questions that are commonly considered in random matrix theory. So the original motivation to look at the eigenvalues of random matrices goes back to work in the 50s when physicists became interested in the statistical properties of the energy levels of heavy atoms. So here's one sort of graph of what that might look like. And the physicist Wigner first proposed using the statistical properties of the eigenvalues of random matrices to model the energy levels of these complicated quantum systems. And then a lot of the interest since then, the one thing that should be noted is that this is actually a very striking proposal to use some sort of random quantity to model this very complicated system, and to look at something like a random matrix to model a physical, very large correlated quantum system. Since Wigner's original work, random matrix statistics have appeared in several other contexts. So they've appeared when you look at the quantization of chaotic classical systems. They've appeared in some connections appearing at the zeros of the Riemann zeta function. And then, of course, random matrix statistics have appeared in describing some of the fluctuations in the class of random growth models lying in the KPZ universality class. And the general belief here is that the random matrix statistics should be these kinds of universal distributions which arise whenever you have a very complicated correlated system that obeys some basic properties. This should be understood in contrast with the Poisson and Gaussian statistics, which characterize systems that have a lot of independence. So then random matrix theory instead asks a simpler question. So maybe we can't directly explain or prove that these statistics are arising in these very complicated physical systems, but can we instead try to understand universality by seeing whether or not random matrix statistics are universal for random matrices? So what does that mean? So the universality conjecture first formulated in Meta's book, Random Matrices in the 60s, is the following. So he conjectured that the limit of something called local eigenvalue statistics of self-adjoint and bind random matrices should have universal limits in the limit of large dimension. And the limits should depend only on what are called the symmetries of the matrix ensemble. So just to fix, excuse me, it's just dry over here today, so I'm coughing a bit. Okay, so there's a few words here. There's local eigenvalue statistics, symmetries. So we're going to work towards fixing what those concepts are. So we'll denote the eigenvalues in increasing order of a random matrix by lambda 1 through lambda n. Then the sort of generic situation that you expect in random matrix theory is that if you form something called the empirical eigenvalue measure of the matrix ensemble that you're studying, then in the limit of large dimension, this random measure usually has some sort of smooth deterministic limit that might look something like this. In particular, there's two basic regimes in random matrix theory. There's how the eigenvalues look at the edges of the support of the limiting spectral measure, and the bulk, so everything that happens away from the edges. So, this measure here, so, this limit of the histogram of the eigenvalues, it describes what's happening to the eigenvalues on global or macroscopic scales. Now, local statistics, it seeks to study how the eigenvalues are behaving on their microscopic or interparticle scale. So as I said, there's two regimes. There's the edge and bulk. So what are the scalings in each of these regimes? So in the bulk, you've got n eigenvalues squished into an interval of length order 1. So that means that the average distance between consecutive eigenvalues is like distance 1 over n. And so one thing you might study is the gap between consecutive eigenvalues. So then you rescale it by a factor of n, and then you get the rescaled gap between consecutive eigenvalues. And then this would be an example of a local statistic that you might study and try to examine the universality of. Now, there's some extra notation we need, which is just that the index I will really denote a sequence of indices which stay away from what's happening at the edges of the support. So they have to, I sub n just has to be away from 1 and n by a macroscopic fraction of indices. And then you can also look at, as well as the k-point correlation functions as well. So remember that the k-point correlation function is just like the marginal distribution of having a k-tuple of distinct eigenvalues at a point. And then there should be one more bullet point on this slide, but I don't know. Okay, you can see it. And then, at the edge, there's the familiar end of the minus 2/3 scaling, and the end of the minus 2/3 is just due to the fact that in random matrix theory, typically the densities vanish like square roots at the edges, which is where the end of the 2/3 comes from. So we'll basically just be looking at what happens in the spectral bulk in this talk. So what I'll start off by doing is just fixing, a pretty general class of random matrices so that we can have some models to ask universality questions about. So a Wigner matrix ensemble is the following example of a random matrix. So it's an n by n self-adjoint random matrix. And then we try to make it as independent as possible, which just means making the upper triangular part independent. If I made every element independent, then it wouldn't be self-adjoint anymore. And then the scaling is such that the matrix entries are all centered and the variance is like 1 over n. So in particular, this is a mean field model where all the elements of the matrix are the same order of magnitude. And then, of course, different choices of the entry distribution give rise to different random matrices. For example, common choices might be taking some sort of discrete distribution where the entries are plus minus 1 with probability 50-50, then, divided by square root n to get the correct scaling or something like that. And then the other famous choice, of course, is when you take the entries to be Gaussian random variables. And then there's two symmetry classes, which are just real symmetric if the matrix entries are real, and complex remission if they're complex. And then the two most famous examples are, of course, the Gaussian orthogonal and unitary ensembles, the GOE and GUE, which are just Wigner matrices where you take real or complex Gaussian entries. So the Gaussian ensembles are very special because they admit a lot of explicit formulas for things like their joint eigenvalue density. And in the 60s and 70s, Godin and Dyson took advantage of these formulas and were able to find various characterizations of the limiting local statistics of the GOE and GUE. For example, if you look at probably the most famous one is the fact that the limit of the k-point correlation functions of the GUE converge to a determinant, which is the sign kernel. And then universality, of course, can be rephrased as if you have any random matrix ensemble, can you compare it to the Gaussian ensemble? Is the limiting distribution of the gap always the same as the GOE and GUE? Okay, so the well-known Wigner Semicircle Law is the following. So, Wigner ensembles are named after Wigner because he's the person that introduced them. And when he did that, he also calculated the limiting global spectral measure of the eigenvalues. So what Wigner proved was that if you take the empirical eigenvalue distribution and you take the limit n tends to infinity, you end up with the semicircle law. And so here's just an example of a histogram of the eigenvalues of a 2000 by 2000 GUE matrix plotted against the semicircle limit. And then, of course, as I've said, the semicircle law, it describes the eigenvalues on global scales. But universality is primarily interested in looking at things like the gap between consecutive eigenvalues. So in 2008, this bulk universality conjecture for Wigner matrices was completely solved by Erdős, Péchet, Ramirez, Schlein, and Yau, and Tao and Vu. And just to give a concrete theorem statement, the following comes from a paper of Erdős and Yau. So what they proved is that if you looked at the eigenvalues of a Wigner matrix, and again, they're just in increasing order, then if you looked at the gap between consecutive eigenvalues and rescaled it by a factor of n to get an order 1 random variable, then this has a limit in distribution, and it coincides with the Gaussian ensemble of the same symmetry class. So this result's actually like from 2012. The earliest results, if they were looking at like the gap between consecutive eigenvalues, actually required a small like local averaging. So it actually took a couple years before universality results for just a single gap with a fixed label were actually available. And there's also a parallel story for a different class of random matrices called the Invariant Ensembles, which can be studied by quite different techniques than what I'll talk about today. Okay. So what I'd like to discuss now is just the 3-step strategy of proving universality, which was introduced in the works of Erdős, Schlein, and Yau. And so I'll give an overview, and then I just want to discuss a couple of the components of these steps. Okay, so the 3-step strategy for proving universality is as follows. So you basically need 3 components for comparing any Wigner matrix to the Gaussian ensemble of the same symmetry class. So this strategy works in pretty strong generality, but for today we'll just discuss what happens in the context of Wigner matrices. So the first thing that you need is the local semicircle law. And what the local semicircle law says is that what it's doing is that it's describing the number of eigenvalues that lie in any interval that's just a little bit bigger than the microscopic 1/n scale. So we're interested in the spectral bulk where the eigenvalues are fluctuating on the scale like 1/n. So we just look a little bit above that scale 1/n and ask how many eigenvalues lie in that interval. And then what the local semicircle law says is that this is basically a deterministic quantity. So it's given by the semicircle distribution. And then there's a very small error here. So maybe you can't determine all the eigenvalues, but you determine it up to a small fraction. And then this estimate has to hold with very high probability. So the local semicircle law implies, for example, the rigidity estimates, which say that if you look at an eigenvalue, it has to be very close to a deterministic quantity, which is sometimes referred to as the classical eigenvalue location, which are just the n quantiles of the semicircle law. So the point of the local semicircle law is to establish high probability a priori estimates, which are then used in other steps of the proof. So the second step is sort of an argument in perturbation theory, which essentially uses either the four-moment theorem of Tau and Vu or the green function comparison theorem developed by Erdos, Schlein, Yau, and Yin. And what this step of the proof shows is that if you're studying some Wigner matrix H naught, then you can use some sort of perturbation theory to compare it to the original matrix H naught, but then perturb a little bit by adding to it a small Gaussian component. So the second two steps use this interpolation between the original matrix H naught and the universal Gaussian ensemble that you're trying to compare the matrix that you're studying to. So the first step is to just show that you can perturb the original matrix a little bit by essentially adding a small Gaussian component to it. And then after you've shown that you're allowed to add a little bit of Gaussian noise, you then are tasked with proving that once you've actually looked at an ensemble which has a bit of Gaussian noise, you need to show that the statistics of those kinds of ensembles are universal as well. And this is sometimes called universality for Gaussian divisible ensembles. And it uses Dyson Brownian motion. So what's going on here is that this interpolation, if your original matrix was a Gaussian matrix, then that would be invariant for this interpolation for all times t. So what this step essentially is that it's a question of can you prove that local statistics under this dynamics are close to their equilibrium distribution after a short time t. In general, if you can prove that you're already close to the invariant measure after a short time t, the smaller times are better. If you want to do something like study the adjacency matrices of sparse random graphs, then in general, you need to be able to prove universality for smaller Gaussian ensembles because you want to make smaller perturbations. Okay, so this is sort of just at a very high level. What I'll discuss a little bit now is just what are some of the components of the proof of the local semicircle law, because it's sort of one of the more basic things about this strategy. And some of the proof ideas are kind of interesting as well. So let me stop. So before doing some actual math, let me stop a little bit to see if there's any questions. Okay, so in the local semicircle law, what we're trying to do is prove that the number of eigenvalues of a Wigner matrix are given up to a very small error by the number of eigenvalues told by the semicircle law. So these quantities here can be thought basically of as like traces, right? Because this thing here is like trace of an indicator function of this interval I of the matrix H. So what that means is that you can actually study both of these quantities via the Stieltjes transforms of the underlying measures. Right, so this this thing here is just an integral transform of the semicircle distribution. And then, this is an integral of the same function, 1 over x minus c, now just against the empirical eigenvalue measure of the Wigner matrix that you're studying. So since this is a tracial quantity, just by something resembling the holomorphic functional calculus, but done for different functions, what you actually have to do is you have to study the difference of these Stieltjes transforms. So the local semicircle law is actually an estimate about Stieltjes transforms. So what you have to do is you want to compare the Stieltjes transform of the empirical eigenvalue distribution to the Stieltjes transform of the semicircle law. And you want to show that this estimate holds with very high probability for any mz is equal to eta, which is just a little bit bigger than 1 over n. So this is the main estimate that one tries to prove when proving the semicircle law. So how is this estimate proven? So the first thing to note is that you can actually, so the semicircle law has an explicit form, and you can actually calculate the an explicit formula for this, for the Stieltjes transform of the semicircle law, and it in fact satisfies a quadratic equation. So then what the main idea is to try to show that the empirical Stieltjes transform satisfies the same quadratic equation up to a little error, and then show that solutions to this quadratic equation, or that this quadratic equation has some stability. So what I'll do for a little bit of the talk is just show how this approximate equation is derived. So this is a trace. This empirical Stieltjes transform is the trace of the resolvent, or Green's function, of the matrix that you're studying. Sorry, I accidentally switched notation. So we'll use W just for Wigner for the rest of the talk. So in order to study the trace of this resolvent, what we use is basically a formula. I mean, this is essentially a consequence of the resolvent identity, but it's it should be viewed as sort of a self-similar formula for the diagonal elements of the resolvent, or the Green's function. So this is something called the Schur complement formula. Basically, if you have a block matrix, it gives you a formula for the inverse of the matrix in terms of the various blocks. And in the application here, what you derive is this formula, right? So this is the ith diagonal element of this matrix here. And what you get is something in a denominator. So first, there's just the diagonal matrix element of your Wigner matrix. And this is small. Wii basically behaves like 1 over square root n. So you more or less just don't worry about it. It's not very big. Then the main term that you have is a quadratic form in the first row and column of the Wigner matrix that you're studying, and the resolvent of the ith minor of the matrix that you're studying. So here, this superscript I means that you're looking at basically the same thing, but now what you are looking at is you're looking at the resolvent, but now of the ith minor of the Wigner matrix. So you remove the ith row and column. And then this sum here just means skip the index I. So remember, what we're trying to do is get this this kind of a formula like this. So we've already found like the minus z. So what we think is that this quadratic form here should be contributing something like this. It should be giving us back the Stieltjes transform that we're starting with. So what I'll do now is explain what goes on with this term. Did I have anything else? Okay. So we have this quadratic form. Now, with this guy, because of the independent structure of the Wigner matrix that we're studying, the ith row and column of it is actually independent from the ith minor, so from the matrix that you get from removing the ith row and column. So in examining this quadratic form, what we should think of it is that it's a sum. Like if we condition on the ith row and on the ith minor, then all of the independence is just in these random variables here, and they have a lot of independence, so we should expect some sort of concentration for this sort of sum. Right, so the first thing we'll do is calculate this conditional expectation, right? So this just means, integrate out the ith row and column of the Wigner matrix W, right? And then, the row of a Wigner matrix is just a bunch of independent random variables. So this expectation is going to be 0 unless these indices here coincide, the j and k. All right, so then you get 1 over n. And what this quantity is that this thing here that you get, this is of course just the empirical Stieltjes transform of the ith minor of W. Now, by Cauchy interlacing, the eigenvalues of a matrix and its minor are just in between each other. And what that means is that, so by Cauchy interlacing, so this sum right, this becomes like a sum over the eigenvalues of the minor of the Wigner matrix that you're looking at. This is actually equal to the empirical Stieltjes transform of the entire matrix, Z plus an error, which is like this, where eta is always the imaginary part of Z. So what this means is that if in fact you do have this kind of concentration, sorry, if you do have this sum that you found in the denominator, does in fact equal this thing, which in fact equals this, then what you see is that you've actually derived the approximation that we were after in the first place, right? Because this is a sum over all these diagonal elements, and then we show that each diagonal element is in fact approximately equal to minus Z minus MN. So if we can show that this approximation here works, then we get this approximate equation. Okay. So what goes into showing this approximation is basically some large deviation estimates for these kinds of quadratic sums in independent random variables. But modulo the large deviation estimates, what we should just try to do is calculate the actual variance of this. So what we basically expect is that since we have a lot of independence here, if we can calculate, if we can check that basically the variance of this quantity is bounded, then it should concentrate, sort of the variance should be enough. It should give us like sort of the right order of magnitude to expect the fluctuations of this quantity around its conditional expectation. Okay. So let's calculate the variance of this quadratic form here. But we're always conditioning on the minor I. So we'll just sort of, with these things viewed as deterministic. Because we're just basically using the randomness in this row and column to actually get the concentration. So what this means is that we're calculating this sum. Like that. And then if we expand this out, so we have to have 4 indices, right? And then, of course, this is just like this. And then we'll do the case that that the matrix entries are real, just for some notational simplicity. All right, then of course you just have to check, when is the expectation on the right-hand side going to be non-zero? Right, so there's of course there's a term when the A, B, and C, and D, when those indices are all the same. The cardinality of that is lower order because, compared to, we have up to n to the 4 different terms. And when they're all equal, that'll just be n terms, so it'll be lower order compared to other things. So then the major terms, what you see is that like, if 3 indices are distinct, then this expectation will be 0. And so the main thing will be when you have something like, it should be, if A is equal to B and C is equal to D, but A and C are distinct, then of course this will be 0 because those terms, because I've taken out the expectation here, right? So the main contribution is a term like A is equal to C and B is equal to D. Or, A is D, but B is C. But those basically give us similar contributions. So what this contribution gives us is, so this 1 over n squared, which comes from the fact that we'll have 4 matrix element powers. And then it's like a sum over AB of GAB I squared. And then now what this quantity here is, it goes back to the resolvent of the matrix itself. So what you can view this as is like, right, this is the same thing as something like 1 over n squared trace something like this. And then this is 1 over n squared, the imaginary part of the trace. Like this. So this whole term goes back to the Stieltjes transform of the minor of the Wigner matrix itself. So what this whole calculation tells us is that if the Stieltjes transform of the ith minor of W is bounded, then we get this approximate equation. So what the issue then is that we need to figure out a way to show that the Stieltjes transform of the ith minor of W is bounded. So the reason that we need this bound is because it comes into the variance of the random quantity that we got in the denominator. And then if we can show that, if we can get that this quantity here in the variance is bounded, then that'll allow us to get this approximate equation here. So how do we get this kind of a priori bound for the ith minor itself? Well, what it is that it's a multi-scale argument where like the point is that what you do is you start sort of with an imaginary part of Z that's at like 2, and then you try to inch closer and closer to the real axis where this quantity can get larger and larger. However, right, this function here, it's basically Lipschitz in the parameter Z. So what that means is that if you have a bound on it at one scale, if you go down just a little bit, you'll get an a priori bound at the next scale. And then you can feed that a priori bound into this approximation, which then gets your estimate a little bit better, right? So the whole iteration scheme is something like, looks something like if so if thing is less than, like, say something like 2, then you get that Mn is an approximate solution of the self-consistent equation to the equation satisfied by the Stieltjes transform of the semicircle law. Then this will upgrade your bound to like MSC plus O of 1. And then you have an estimate like this. So that tells you that, in fact, this might be better than like 3/2 or something. And then you can go down to the next scale and feed that estimate back in and do the sort of iteration argument. So maybe just summarizing what goes on here is that, so here, let's actually go to this. No, sorry. Okay, so again, so the main point for, so just to talk about the local semicircle law again, the main point is that we're trying to compare the Stieltjes transform of the matrix we're interested in to the Stieltjes transform of the semicircle distribution. Now, this thing satisfies this equation like that, and the Stieltjes transform of, and so what we're trying to do is we try to show that this empirical Stieltjes transform satisfies this approximate self-consistent equation. And the main tool to do this is this Schur complement formula, which allows us to rewrite the diagonal elements of this resolvent in terms of a quadratic form involving the ith minor of W and the resolvent of the ith minor, so as the ith row and column of W and the resolvent of the ith minor. And then what we need is some sort of concentration of this quantity around its expectation. But that itself requires an a priori bound for Mn. So the reason why you need some iteration argument is because you need to feed that a priori bound from larger scales into lower scales to make this thing close. Okay, so that's everything I want to talk about the local semicircle law. So in the last 10 minutes, we'll talk a little bit about Dyson Brownian motion. But maybe there might be a question about what I talked about so far. So let me pause just for a moment.
So maybe if nobody has a question, I want to ask a question. So this estimate on the quadratic form that you showed, they were given for GIK as like a deterministic function. But the GIK depends also on the W's. So how do you justify it? Yeah, so I don't have the intuition to say that the same estimate work even if the Gij is not deterministic anymore.
Yeah, so it's I mean, the point is that so if we're just looking with I is equal to 1, so then here G1, like this is this row here, and then so this is just the structure of what you're looking at, right? And So, right, if you condition on this, then this is just, I mean, this is independent of everything in here. That part's okay, right? This is just how we set up the Wigner matrix, that this row and column of the matrix is independent of all the stuff here.
Yeah, because the summation excludes the.
Yeah. Now, so what the point is that like you condition on this, and then you ask for how much does this concentrate around its expectation. So there's like sort of two levels of randomness where you basically assume that like these things are bounded. That assumption, only depends on this. And then on that event, you establish some concentration of this quadratic form. So that's what happens. So like you have an event on which you have some estimates, and then conditional on that event, there's some concentration. So you lose a little bit of probability, but just all of the estimates, because you're basically assuming that there's as many moments as you want, all these estimates will hold with like very high probability, like something like -n to the 100. So you have to do this argument like several times, but it'll only be like n to the 4 times or something. So that union bound you won't lose.
Okay. Thank you.
All right, so in the last like maybe a few minutes, I'll just give some discussion about Dyson Brownian motion as well. So one of the other steps of the 3-step strategy of pioneered by Erdős and Yao is, so what they want to do is study this interpolation between the matrix that you're trying to study and, say, a matrix from the Gaussian orthogonal ensemble. And what they are trying to show, what you tried to show is that after a short time t, the eigenvalue statistics of this interpolation already get to the invariant measure, which is the GOE. Of course, right, when t, is like n to the epsilon, then since you have like, since these are exponential, like everything is gone. So then WT is already like GOE, but need to show that like with t being, something like n to the 100 over n, already we have the gap statistics of WT are close in distribution to those of the GOE. So what this is that it's a question about approach to equilibrium. If you look at a very specific observable, so the gap statistics, so you know that for very long times, since you have like e to the -n epsilon, for very long times, everything is already going to be close to the GOE. So what local ergodicity is that it's a question about, if you look at gap statistics, will they already be close to the equilibrium distribution after a much shorter time, t basically a little bit bigger than 1 over n. And the way that this part of the argument goes is by reinterpreting the eigenvalues of this interpolation as a dynamical process, which is known as Dyson Brownian motion. So what Dyson's calculation is that he showed that the eigenvalues of this interpolation WT. They have the same distribution as the solution to this system of stochastic differential equations. So these are the eigenvalue evolution. And there's some Brownian motions here. There's parameter beta that depends on which symmetry class you're looking at. So for example, if you're interpolating to the GUE, then beta is 2. If you're going to the GOE, then beta is 1. And then the main term here is that there's a long-range singular interaction term, which repels the eigenvalues from their close neighbors. What the miracle of Dyson Brownian motion is that the eigenvalue evolution depends only on other eigenvalues. There's no reference to eigenvectors in the system of equations whatsoever. And that's the miracle of this calculation. Okay. So, and now what Dyson's conjecture is, and what I alluded to just in the previous discussion, is that as we saw, it takes times order 1 to reach equilibrium on global scales. Dyson conjectured that it should take only a very short time for local statistics like the eigenvalue gap to reach equilibrium. So for example, what he expected was that after t being a little bit longer than 1 over n, we have in the limit n tends to infinity that if you look at, for example, the expectation of a smooth function of the gap between consecutive particles, then as long as t is a little bit bigger than 1 over n, then this expectation should already be close to the distribution of the invariant measure. So maybe in the last 2 minutes, let me just give a heuristic about where this 1 over n scaling comes from, because it looks a little bit mysterious. But what it's explained by is just the Brownian scaling and the first term in the expression of dBm. So as we saw that in the bulk, the distance between consecutive particles is about 1 over n. And this the SDE for Dyson Brownian motion, its first term has a dBi in it. Right, so how much mixing is there after time t? Well, after time t, right, you know that due to the Brownian scaling, this is like square root t over square root n. So the question then is like, how long do you have to wait before the random Brownian motion term pushes the particle enough so that it mixes with its neighbor sufficiently, right? So what that means is that you need this Brownian term to bump the particle distance 1 over n so that it mixes with its neighbor. And then if you solve this, this is just where the 1 over n scaling in the bulk comes from. And then, if, for example, you're interested in like edge statistics, where everything is like 1 over n to the 2/3, then the same argument gives you that the time to equilibrium at the edge is like 1 over n to the 1/3, for example. So it's just where those scalings at n come from. Okay, so I think that's about all the time I have in this talk. So let me just stop there. And then if there's any more questions, I'd be happy to answer anything you might have.
Oh, thanks, Ben, for the nice talk. So do you have questions for Ben? So I have a few questions about this last thing. So how does this heuristics helps to So I can understand like 1/n is the right scaling, but how do you conclude like if we take something slightly bigger than 1/n, then we will have this convergence?
It's just like sort of it's just like the right sort of time scale. Because sort of what you should view it is that like I mean the proof doesn't use like these heuristics whatsoever, but kind of what you should sort of what you can think of is that like if like the sorry if you go to sort of like natural coordinates, then basically like wow, that's not what I wanted. Sort of what a particle kind of sees is it sees this sort of entire other array of particles that sort of go off to infinity in its like time scaling. So like because if you're like sort of rescaling things so that you send like xi to like nxi, then what each sort of particle sees is that like a big lattice of other things approximately distributed like that. And then in this kind of scaling, the dBi over like square root n really becomes like just dBi, like just a regular Brownian motion. And then when you've done this rescaling, like sort of where all the n dependence is that it's like way out at kind of the edges. It more sort of becomes like how many particles there are. So with this kind of a system, sort of like what you see is that there's no kind of n dependence. It's just like one particle sitting in like what's essentially an infinite like lattice of particles. So then here, what you expect is that as long as there is some sort of convergence to equilibrium, as long as t is like much, much larger than 1, then you should get to some sort of equilibrium distribution. And then just undoing all the scalings just gives you that t should be much bigger than 1/n.
I see.
Hey, Ben,